Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. So we are going through a very important part of this finite element analysis, the development of elemental equations under the assumption of particularly the finite element approximations. And so we are trying to illustrate it with respect to the one-dimensional example. So where we have taken a very simple example here. So a second order differential equation with some boundary conditions here, and then the weighted residual statement looks like that. Of course, here what we assume at this moment is that the phi hat is satisfying the given boundary conditions phi a and phi b at x is equal to 0 and 1. So we are trying to develop it, and then the weak form of this one turns out to be this one, where the derivative on phi hat has been reduced to 1, so it's a first derivative. And then with the background of a lot of discussion which we had in the last class, so we said that though apparently this seems to be should be continuous, but then the continuity requirements have been reduced, and to the point that d phi hat by dx may have finite discontinuities, in particular at element boundaries. And d phi hat by dx, of course, will be continuous within the element, and at the element boundary, we relax it so that it can have some finite discontinuities. So if d dx has finite discontinuities, then we say that the phi hat is C0 continuous. So if phi 0 is C0 continuous, then the derivative may have finite discontinuities. Okay, so according to that, so the simplest approximation which we would like to have, there are three elements which we had 1, 2, 3, 4, and omega 1, omega 2, omega 3, and then in each element, so we would like to have at least a linear approximation so that the first derivative is existing, will exist. So in different phi 1, so this is phi 2 and this is phi 3, and the different domains. So the domains are x1 to x2 in omega 1, and it is in x2 to x3. So this is the thing. So the beauty of this approximation is that the nature of the approximation within each element remains the same. Of course, the coefficients will be different, that's all. But apart from that, the nature does not change. And then, so if this is what's going to happen, so then what we say here is that we have the constraint that at 2, this will continue here. Okay, with the 3 elements like this one, maybe this is a little longish. Let's make them equal. It's not necessary. Okay, so what the constraint says is that phi 1 and phi 2 at x is equal to x2 should be same, and so similarly here phi 2 and phi 3 at x is equal to x3 should be same. So that's how the conditions are. So that means that we have one condition, something like the conditions, if I put it like this one, So this is one condition. And then another condition is at x3 So that means that we have, if you look at the approximation, we have 6 constants, right? And then we have 2 constraints coming because of the continuity. And then the other 2 more constraints are coming because of the boundary condition, phi is equal to phi a, phi b. And then that leaves 2. So the 2 final equations will come from the weighted residual thing, in the sense that taking weighting as the corresponding to 2 W2, there will be one equation, Wi being equal to W3 will be another equation. So that way we have 6 equations, 2 from here, 2 from here, and 2 from here. So there are theoretically well posed, it says 6 equations and 6 unknowns. Okay, so that sounds pretty straightforward, well posed. But on the other hand, is it possible to reduce the number of equations? So we would like to reduce the number of equations from this point of view. So that means that at 2, so this is what we said, right? And this is at 3. So instead of that, so is it possible to reformulate this approximation in some other constants, but still keeping the linearity within each element? So let's look at that one. So what we are saying here is that we are going to use this one, okay? So what we need here is that instead of writing it in terms of A1, B1 and A2, B2, A3, sorry, this is 3 here, A3, B3. So what we would like to directly do is that, is it possible that if you call this as phi 1, phi 2, phi 3, phi 4 like this. So we would like to rewrite this phi hat, say in phi hat 1, we would like to directly write it in terms of phi 1, phi 2, so such as phi 1 plus phi 2 minus phi 1 divided by x2 minus x1 times x. So this you can see that it is having a variation of phi 1 to phi 2. So this is in the region of element 1, right? In the region of 2, so we can similarly write exactly the same thing like this. So and phi 3 here, similarly in the third domain. So we have this. Okay, so this way, this is consisting of phi hat expressed in different zones. This is in x1 to x2, and this is in x2 to x3. So if you look at these expressions, okay, so the unknown values here are phi 1, phi 2, phi 3, just like A1, B1, A2, B2, A3, B3. So instead of A1, B1, A2, B2, A3, so we have the unknown coefficients phi 1, phi 2, phi 3, and the rest of the things are all known. So let us write this one, rewriting. So we will just put it in a much more concise manner. So here we'll write it as, look at this one. So this is just recollecting those things. So that means that here these things are collected at one place, multiplying with phi1, phi2, right? So obviously at x is equal to x1, okay? So this part turns out to be 0 and only this one turns out to be 1 and only leaving phi1. So similarly in the zone 2, we have exactly the same thing. I'm just writing it for the sake of completeness. And this is 3 in the third zone. So this is what's going to be x4 minus x . Okay, so this is now writing it, the recollecting these collecting terms phi1 and phi2. Now we wrote it neatly in terms of phi1, phi2, phi2, phi3, phi3, phi4. Of course, obviously in different domains. So writing this in this form, there are two features. One is this phi1, phi2, phi3 are taking the place of the coefficient bi's, right? So now the expression here, instead of this psi naught plus bj psi j, j going 1 to n, so those bj's are now rephrased as phi1, phi2, phi3, phi4. So that means that when you solve the problem, so you will get phi1, phi2, phi3, phi4. So that is one thing. And then this also offers a tremendous advantage. So instead of the coefficients bi's, so now we are directly getting the coefficients phi1, phi2, phi3, phi4 once you solve the problems. What is this phi1, phi2, phi3, phi4? So these are nothing but the nodal values of the function phi at the 1, 2, 3 and 4. So here I'll just write it. So the advantage is here. The expression phi hat is directly in terms of phi i's. Okay, so which are when solved, when problem is solved, are the values of phi hat at nodal locations, at so this is a very special advantage that when you want to calculate phi hat in the earlier approach, so you get the solution phi hat in terms of the coefficients and psi i's. Now you have to substitute the values of x in psi and multiply with the coefficients so to get the function value at any other point, right? At any other point in the domain. So now what we have here is that if you are interested in the value of the function phi at primary locations, the nodal locations, then you can directly get it. So that's the advantage, right? And of course, That's number one. Number two is, of course, that this is piecewise defined continuous functions. Another thing is that what is the equivalent of psi here? So the one before the coefficient is nothing but the psi. So so we can write this one. So we will rewrite this. So this is a tremendous advantage. So rewriting above equation. So in a concise manner, so we will write phi1x as n11. So we'll just writing that, and okay. So that means that these functions, we are renaming them as n1, and this also has superscripts 1 because this n2 here is repeating, right? So this is n2 of 1, n2 of 2. So they have different expressions. And so similarly n3, 2, and n3, 3. So because n3, we are putting it because it is the coefficient corresponding to phi 3. I mean, function corresponding to the coefficient phi 3. So like this. So I don't have to rewrite, saying that now I can say that this n11 is nothing but x2 minus x by x2 minus x1, and n21 is x minus x1 by x2 minus x1, and so on. So let us also see now, interestingly, what are these functions and how they look like graphically. This is very important for us. And also I can remind you now, so the number of unknown coefficients, earlier we said that there were 6 coefficients, a1, b1, a2, b2, a3, b3. Now we have how many coefficients? We only have, in fact, that is one of the advantage, the number of unknowns. So in fact, that also should write here. The number of unknowns here have been reduced to only the nodal values. So we don't have 2 unknown coefficients for each domain. So okay, so in fact, if you want, I can also write it. This is 1. The other advantage, number of unknowns. This also, I am just mentioning it, or reduced. So this is another very important advantage. So that's what. So now let's get back to the shape of 1, 2, 3. x1, 1, 2, 3, 4, x1, x2, x3, x4. You can write it as x1, x2, x3, x4 if you want. Okay, so this is omega 1, omega 2, and omega 3. All right, so what is this n1? For example, if you take this phi 1, so it is defined only in the zone 1, and it has a, let us say this is n's. So this has a value of, if you can see that expression. So if you just recall that n1, I will just write it for the sake of convenience. So it is x2 minus x divided by x2 minus x1. So what is that? That has a value of 1 at node 1 and a value of 0 at node 2, and then it varies linearly with x. So it is like this. So the function here is obviously defined only in the domain 1, and obviously it is 0 elsewhere. Okay, so this is what n1 is. N1 belong to zone 1 only, right? So this is n1. What about this n2? So similarly, n2 expression of zone 1 is x minus x1 divided by x2. So that means that this n2 will be having the expression like this. So it is having 0 here and going to 1 there, and then it is 0 here. So this is n2 defined to 1. Okay, so like this we have n2, and then we have like this. We also have other things. So if you look at the domain 2, okay, so then this is the domain 2, x2 to x3. So similarly here we can say that it is going from this n2 of 2 will go like this, and this is n3 of n3 of 2, right? So this is for phi 2, right? So similarly we can continue, and in the zone 3 we have this is n3 in zone 3 and n4 in zone 3. Okay, so this is how these functions are defined, and these are defined only in those subdomains. And now let's look at, interestingly, let's look at these things a little bit. If you look at closely, then what we can write the function phi hat, for example, phi hat overall so what we have here is that if you combine it, so we can write it as n1 okay, we combine it, so I'm combining them, n3 of 3 plus n4 of 3 okay. So nicely we can write it. Slowly we are step by step we are coming close to the original expression given by in terms of B. So what we have here is that phi 1, phi 2, phi 3, phi 4 are the coefficients, and the ones before that are the approximations, okay, corresponding to that node. Okay, so this also can be written as N1, phi 1, N2, phi 2, N3, phi 3. So we can also write it in this fashion. So interestingly, let us see what these are: N1, N2, N3, N4. So if you write it n's, nice, let us see, and we have it N1. Let us say, first of all, let's take N1. So if you take 1, N1 has, look at this one, N1 is like this. It consists of the only non-zero expression in 1. So that means it is like this and 0 everywhere. So this is the overall expression. So similarly, we can also say what will be N2. So for N2, so what it has two definitions, N2 in 1 and N2 in 2. So N2 in 1 will be like this, right? So that's what we have, N2 in 1, and this is N2 in 2. So this is the expression for so this is N2, right? And so similarly we have this is N3, so I don't have place here. So can you now extrapolate what N4 is? This is N3. N4 is only defined to be non-zero only in the domain 3. So how will it be? I'll just draw it here now that you know all these expressions. So this is N4. Okay, so these are called trial functions, or even they are called or the terminology here, common terminology is shape functions. These are all called the shape functions. So the one important feature of these things is that N1 goes from 1 at node 1 and goes to 0 at the neighboring node, and 0 or everywhere else. So similarly, N2 here is having a value of 1 here, and at node 2 and goes to 0 here at node 1 and goes to 0 at node 3, and everywhere else it is 0. Okay, so similarly N3 is having a value of 1 here and 0 at 2 and 0 at 4. N4 I have written it right here. So now that you have understood, the N4 is having a value of 1 at node 4 and at 3 it is 0. So this the interesting part here, as we have been saying, that the trial functions or the shape functions, so the one important feature is that they are defined over a very small domain, either in one element or two elements, right, in one element or two elements, and everywhere they are 0. So these are all very compactly defined. So they are non-zero over a very compact, over a very small domain of the total problem, right? So N2 is only non-zero on omega 1, omega 2, N3 is non-zero on omega 2 and omega 3, and 4 is 0 over N4 only. So that way, the two important features here are these shape functions, okay, in the finite elements point of view, or the trial functions from the mathematical point of view. They are defined over a very small domain, okay, very compact. That's number one. Number two, there is a very important feature of this one is that the expression for these shape functions is very, very simple. For example, here this shape function is having an expression like what? It is having x2 minus x divided by x2 minus 1, x1, right? And so the same thing holds good for this also. For this also it has the same expression. So for this one here, it is nothing but x3 minus x divided by x3 minus x2, and the same thing here. So these shape function expressions are very repetitive, or exactly they are same. So if you can find out the value of these weighted residual expressions, so they are, if you want to do it here and here and here, so they are all very repetitive or very, very simple. So this is the beauty of these kind of piecewise approximations. Number one, a repetitive type of expressions that's very locally, compactly defined. So that is another number two. So that is why. So, and then since they are very repetitive in nature, then whenever we are going to do the calculations, develop the algebraic equations, then the developmental or coding process is very repetitive and can be concisely written. So we'll, in our next lecture, so we are going to take this one and try to solve this problem. So for the moment, we'll stop it here. Okay, bye.